In this video, I'm going to describe the aspects of Flames memory management with which you need to be familiar as a Flames software developer. This is probably the most important of all of the Flames software development guidelines. Memory management is extremely important, and if you don't follow the guidelines that I present in this video, you will more than likely run into some pretty significant problems. Memory management in any large software system is one of the most important aspects of the system, and we put a lot of energy into the software that we've written to manage Flames memory, and that makes a really big difference. One difference is the performance of the system. The other one is the reliability of the system. Another is the ability for the system to scale, to get larger as the scenarios get larger. We have successfully executed scenarios in Flames that have over 1 million units and 1 million players, and that's because of the fact that we have a very robust way of managing memory that's part of it. Flames memory management also has built-in ability to detect memory corruption. If you work with a system that dynamically allocates memory, you know there's always a potential that memory would get corrupted, and sometimes finding corrupt memory is really difficult. And if it's not found, if it goes on undetected, it can crash your program or invalidate the results. So we have a lot of extra capability in our memory management systems to be able to detect memory corruption. We can also help you find memory leaks. And perhaps most importantly, if you follow the rules that I'm going to describe in this video, your software will be compatible with the 2 Flames options. One of them is the Flames checkpoint restart option, and the other one is the Flames multi-thread execution option. Memory management is very important in order to be compatible with those options. The information I'm presenting today is found in one of the developer's manuals, like the rest of the videos in this course. I'm in the Flames development guide, and I'm in the section on memory management. I'm going to cover all the information that's in here, but if you forget it or if you want to read and get it reinforced, it would be a good idea to read the topics in this manual. So first of all, some general memory management rules. The first is that memory for all variables must be dynamically allocated. So declaring fixed arrays of things, we can have this many of this and this many of that, and hard code the value to some fixed dimension is not in keeping with our guidelines. We have to dynamically allocate everything. There are a few exceptions, however. Of course, automatic variables within a function don't need to be dynamically allocated. They're dynamically allocated by the system, so that's an exception. If you have a global or a static variable that has values that don't change after the initialization of the class, then those variables do not need to be dynamically allocated. And a lot of times we declare default structures, for example, in Flames, and you'll see that in the Entity Model Developer's Manual. There will be a default structure that gets initialized during the initialization of the class, which is something that takes place at the initialization of the beginning of the execution of the application. A lot of values get set in those global structures, but those values never change after class initialization. So it's okay that those variables are not dynamically allocated. And then certain times we use a static variable to pass information between functions, and the values don't need to be preserved from one function call to the next. So they're just little workspace variables that are only used within a function, and once the function returns, it doesn't matter what their values are. Those are legitimate for non-dynamically allocated variables. So those are just a few exceptions. With just those few exceptions, everything else needs to be dynamically allocated, and all the Flames software all does that. And if you're copying and looking at the Flames models that are in our repositories, they of course obey all of these memory management rules. Now the next big rule, and this is probably the most important of the rules, all dynamically allocated memory, which again is pretty much everything in the system, must be allocated and freed using Flames memory allocator functions, memory management functions. Flames has a whole bunch of memory management utilities, and you are required to use those in allocating your memory for your variables. And we're going to talk more about those later on in this same video. This is extremely important. If you violate this, you will absolutely render your software incompatible with the checkpoint restart option in Flames. Now, if you don't care about being compatible with that option, then you can break this rule, but you'll also give up on a lot of the advanced memory management features that are built into our memory allocators. But if you ever think that your software might get used with checkpoint restart, then you need to make sure you use our allocators. Now, there is an exception to this. If you're allocating memory that is not used during scenario execution, so for example, it's just used when you're editing the user interface, that memory would not have to be allocated with Flames allocators. We always allocate memory with just very few exceptions from the Flames allocators. And so if you always do it, then it doesn't matter. But there are exceptions. If it's just done during scenario editing, we don't do checkpoint restart in the editing applications. We only do checkpoint restart during scenario execution. So using our memory allocators is only absolutely required if it's code that's going to be executed during execution. And the reason we do that is our checkpoint restart system is automatic. It automatically checkpoints, makes a copy of all the memory in the application at a checkpoint. And it does it automatically, so you as a developer don't have to write any code in order to get all the memory that you've allocated automatically saved to a checkpoint file. And then it automatically restores it when a restart occurs. That only works if you're using our memory allocators. Another rule is that all dynamically allocated memory must be freed. So that prevents memory leaks. And we've got a tool to help you find memory leaks built into our memory allocators. And there's instructions in this manual on how to do that. And then finally, this is a real subtle, but it's a very important thing. If you want your code to be compatible with the multi-threaded option, you have to make sure that all of your functions are thread safe. And there are quite a few things that go into making your functions thread safe. If you write your classes the way that we tell you to in our development documentation and in our training videos, your code will be thread safe and it will be compatible with Flames multi-threaded execution. In order for multi-threaded execution to work the way it should, you should get exactly the same results when you run in parallel, when you run multi-threaded, as you do when you run single-threaded. If you have a system that doesn't do that, then you can't have any confidence in the results that are produced when you're running multi-threaded. So basically, multi-threaded execution is for simulations, is essentially useless. Our system produces identical results when it's sequential or multi-threaded, and it's in part because of the way that we manage memory, which is one of the things that's necessary. You can read this in this topic here, but what it means is that when you write a given function, you have to be sure that that function can be called simultaneously for two different objects, and that those simultaneous executions are not stepping on each other's memory. So that's a big part of making your code thread safe. Again, if you'll follow all the guidelines and instructions that we have for writing code that's throughout our manuals, that will be taken care of. But the general rule is you got to make sure your code is managing memory in a thread safe way. So let's get on to the specifics of the memory management implementation, memory management rules. And the first one is memory management functions. All the functions in Flames for managing memory are named like this. There's a mem allocate, a mem free, and a mem resize. And the prefix of that will depend upon which allocator. We've got a bunch of different allocators. So we've got atmosphere memory, basically one allocator for each primary class of model. So we've got atmosphere, attribute, cognition, effect, equipment, service, temporary, and view. And so those are the memory allocators that are available to you, and each one of those has a allocate, a free, and a resize function. The arguments to these functions are very similar to the calloc function. So they're really easy to use. Again, if you go to our code in the repositories, all of our code is using all the proper memory allocation functions. And if you go through the documentation on how to write a particular model, that documentation will tell you to make sure you use this particular allocator, so you don't have to try to figure it out here. This is just an introduction. We'll talk about it more in the other software development manuals. The one thing that's important here, and I actually need to go back to the rules, when we say that all memory has to be allocated from Flame's memory management functions, one of the things that means is if you're using a third-party library during scenario execution that internally is allocating some memory, and it's done in memory that needs to persist, it's not something that it is one of these exceptions that I mentioned earlier, you can't use that library. Not if you want to make sure that your code is compatible with the things that I've talked about. If you don't care about multi-threaded execution or don't care about checkpoint restart, you can break these rules. Also, if the normal new operators for C++ classes, when you define a C++ class, they normally go out and get memory down internally. It's hidden from you. The system is getting the memory, but it's not getting it from Flame's memory allocators. So if you write a C++, your own C++ class, and you use its new operator and you don't override that new operator, you've just violated Flame's memory management rules. That's one of the things you have to be careful about when you're programming in C++, because there's all these little tools and utilities and things that are in the standard C++ libraries, and they all do memory allocation, and you can't use them unless you're able to override the way they allocate memory. So we have our own set of tools in Flames that provide us all the functionality that we need that are allocating memory correctly. We also make sure that all the Flames classes, the C++ classes that you inherit in your models, in all of those classes we have overridden the new and delete operators to make sure that they are using Flames memory management allocation. So if you're inheriting our classes that are in C++, that's taken care of automatically. And one of the things that we have here is we've actually overridden the new operator. The new operator is there and it works, but we have another operator called fnew, and that operator adds some additional functionality to the new operator. Basically adds additional data to the memory allocators to know where that memory was allocated, so that we can produce that information in the case that that memory ever gets corrupted, or if we ever want to do automatic leak detection. So you'll see that fnew operator talked about, and it's universally used in the allocation of all of our objects throughout all of the code in the repository. So this is where we mention that and explain why it's there. You can use the new operator again, but we recommend you use the fnew because it provides additional functionality. So those are the rules. Those are the things that you need to know about. So the rest of this manual just talks about, or the rest of this video talks about some of the features of the Flames memory management. One of them is automatic error detection. And we're always checking errors every time memory is allocated or resized or freed. We're always looking at the memory pools and the memory headers and making sure that somebody hasn't overridden things. We can't detect every possible memory corruption, but we can check a lot of them. And it happens when we allocate and free. So this topic gives a little bit more detailed information if you would like to read the details about what we're catching and how we catch it. When we catch those errors, we actually report them. So messages get generated, and the messages are real informative because our memory allocators all keep up with the exact line of code where the memory was allocated, wherever any memory was allocated. And there's just a few exceptions to that. When an error occurs, we can tell you, hey, we just detected a leak at this line of code, in this file or in this function. And if the memory is corrupted and it was in another place, we can say, well, this is the memory that's corrupted and it was allocated over here. So because our allocators have this additional capability built in, we can provide those more robust messages. And I've had lots of memory corruption problems that I found instantly because of the error message that was generated by the Flames memory allocators. Sometimes memory allocation is not detected because a given free operation doesn't stumble upon the place where the error is present. So we have this function here where we can turn on enable validation, and what that does is, and you can read about this here, if you call this function and turn this on and pass in a value of true, ftrue, then all the memory of all the allocators is checked every time there's a memory allocation problem. So if you have some kind of an error and you can't find it, you can call this function somewhere in the initialization of the application in one of your class initialize functions, and then run it. It's going to run quite a bit more slowly when this occurs, but it will check, again, it checks all the memory every time any memory allocation occurs. Normally when you're doing an allocation, it only checks the memory around the memory that's being allocated, or around the memory that's being freed. But this will check all the memory every time something happens. You can also make a call to check, validate the memory on demand. So this will cause it to occur not when a memory allocation operation occurs, not when a memory is allocated or free, but if in between allocations and frees you want to check, like maybe you go down through and you know an error is occurring at a particular line. So you can sprinkle calls to this particular function in your code, and it will check it on demand. And again, it checks all the memory in the entire system. And that call will almost always help you identify the problem in the memory very quickly. And again, whenever it detects some corrupted memory, it will tell you where the memory that was allocated, where it was allocated in the code, what line number and what function or file. Again, that's a built-in feature to our memory allocators. Similarly, we have leak detection. Now, we don't run leak detection all the time because it's very time consuming, but we have a tool in Forge that can be used to detect leaks, and because Forge can execute scenarios, it also will check memory that's being used in Fire, because Fire is executing the same code when it executes a scenario that Forge does. So the detailed instructions on how to use the memory allocation is, and the leak detection is, those instructions are in this topic, so I'm not going to go over all these things, but it gives you just a procedure for how you would go through and look for leaks. When we first got this implemented and we ran it on all of our models and all of the Flame system, we were humbled by the amount of leaks that were there. And this tool just tells you exactly which memory was allocated, where it was allocated, so that you know that's the memory that you need to make sure it gets freed. So it's very handy, and we would recommend running this periodically. Maybe after you get done with the major release of your software, go run this leak detection tool. It's particularly useful when you're running the enhanced analysis option. The enhanced analysis option, if you know anything about that, you can feed it an experiment file, and this is an option that's available in Fire. And Fire will automatically run the same scenario over again with different design cases, and it could run a given scenario 10,000 times. So it runs it, resets it, runs it, resets it with different design variables. It's extremely powerful capability. Well, if there's memory leaks in your models and you're running a scenario 10,000 times, it's very likely that when it's over, or sometime during execution, you're going to exhaust the memory on your computer. So this is a way to find the memory leaks and make sure that doesn't happen. We also have applications. Forge has a built-in ability to, for example, run a given execution over and over and over again, and with graphics. And that's a feature that we use when we take Forge to trade shows. So we'll set up a scenario and we'll hit play and we'll just let it sit there in the booth and just run. And sometimes it's running from morning till night. It'll run 8 or 9 hours just constantly over and over. And it may be just a 2 or 3 minute demo scenario, so it's running hundreds of times. And if you've got leaks in your memory, eventually the application would crash because it Each time it resets, you would have memory that's not getting freed, and it would crash. So this is a really, really useful tool, and it's one of the key advantages. The automatic error detection and the leak detection are two of the really key advantages to the Flames memory allocators. Something else, our memory allocators are generally way faster than the system memory allocators. If you've ever done work in writing memory allocation algorithms, they can be very complicated, and it's difficult to write a general purpose memory allocator that's also very efficient. So we have different kinds of memory allocators that we use in different cases, and some of them are just blindingly fast. They can be literally thousands of times more efficient than the system memory allocators. They're extremely efficient. So it's another advantage of using our allocators. So those are the rules, and those are some of the benefits. Again, this is really important. And if you're paying attention to the ways that we tell you to write software, all these rules are abided by in all the rest of the documentation and all of our code. Thank you for watching this video, and we hope it's helpful. And thank you for using Flames.